So we'll have neurotransmitters either tomorrow, which is Thursday, or on Friday. What do you say? Would that be okay? Okay, tomorrow or Friday. So as I said that, giving my Friday to you all. Definitely not. I don't mind giving extra time to you. Don't think that it's a Friday and it's going to disturb you. Of course not. Of course not, right? So I'm perfectly okay with it, right? As long as you will be benefited, I'm going to be okay with you. But as I said that, I didn't want to do hodgepodge and finish all the three chapters just for the sake of, okay, I have to finish all the three chapters. So it's not just a revision class. It is, I'm going to teach you, full fledged. So it's not just, if it would have been just a revision class, I could have skipped the slides and, move on and finish three chapters within 3 hours. So we'll just try to finish both the chapters by 12, inshallah. God, as I said that, I don't mind here. I don't mind to put extra effort for you. It's okay with me, even if it's a Friday. Trust me, it's okay with you. If it's okay with you, that's okay with me as well. You tell me what is best for you. If you're comfortable with Friday, I don't mind doing that on Friday. Don't worry, I'm there. I'm there to to provide an extra help. But you also need to work hard and inshallah bring good grades, and you need to study so that inshallah you can have good grades. Okay, so both of us have to, all of us have to work hard. I don't mind doing my part. Okay, so you're okay with Friday. It's perfectly okay. So we can fix the timing either in the morning or in the afternoon. Okay, I will let you know. So again, we'll have the attendance is, because it's an extra class on Friday. Okay, so the attendance is not mandatory for Friday. So if you would like to join, you can join on Friday, and then people who are unable to join on Friday, they can listen to the recording in the evening. Okay, would that be okay? Okay, everybody is okay with Friday. Okay. Okay, so we're going to have neurotransmitters is a very easy chapter. Okay, so I'm sure that will not take a lot of time to finish it up. So Friday should be okay. I'm okay with Friday. I will let you know the timing, Island. I will upload the timing on Moodle, okay, for the Friday's extra class. Okay, don't worry. Okay, so let's begin with the chapter proteins. So in proteins, the first and foremost thing what you need to know is that you have to ask yourself why I'm studying proteins. What is the reason? Okay. If you ask yourself this question, why I'm studying proteins, the first and foremost thing you will get an answer that I find proteins everywhere in the body. My body is nothing without proteins, isn't it? If you see collagen present in the connective tissue, keratin present in your nails, in your skin, in your hair, n number of reactions in our body, right? Oxidation, reduction reactions, oxidation of food, production of ATPs. Everywhere you have enzymes. And what are enzymes? Enzymes are nothing but the proteins. Most of the enzymes are proteins. Yes, we recently spoke about antibodies, defense mechanism, protecting us. They are proteins. We spoke about how muscles move, right? We spoke about how important actin and myosin is last semester, right? Binding of actin and myosin, and how muscles can move using actin and myosin, right? So movement is impossible without actin and myosin, which is nothing but they all are proteins. How can we ignore the role of hemoglobin? We know that without hemoglobin, the oxygen cannot be transported. Okay. And the oxygen transporter is nothing but your Mr. Hemoglobin, which is again what? Which is a protein. Hormones, we spoke about chapter number 9. Oh my God, how many hormones have a protein base? Except we just have handful of steroid hormones. Rest all the hormones are either peptides or amines or proteins. So peptides, by the end of the day, they are also proteins. So insulin, oxytocin, human growth hormones, like there's so many hormones which are nothing but which belong to the category of proteins. protection, as I said, antibodies, fibrinogen, conversion of fibrinogen into fibrin, okay, whenever there's, God forbid, any injury in the body and blood needs to be clotted. What is it? It is a protein, okay? If you need to store extra iron, okay, in your body, okay, iron is a part and parcel of hemoglobin. That iron is also stored in the form of a protein called as a ferritin, okay? And how can we ignore that when a newborn, when the sperm and the egg fuses, right? It is the protein ovalbumin, right? Which actually provides nutrition to the embryo. Casein in the milk proteins, right? They are also proteins. And finally, so many, we spoke about recently, we spoke about transcription, we spoke about translation, replication. Did you see how many enzymes we spoke about? Helicases, topoisomerases, DNA polymerases, RNA polymerases, all these are enzymes and they're nothing but the proteins. So in short, we are nothing without proteins because proteins make up almost 3/4 of our dry weight in the body. Can you believe? That is why proteins have been given a name called as a proteose. Proteose means primary. Primary means, which is so very important for the body. So that's why proteins are very, very important for the body. Did you understand the importance of protein? It's like everywhere. We're nothing without the proteins. And now, if somebody is going to ask you, name the elements which are present in proteins, you're going to name, right? You're going to name carbon, you're going to name hydrogen, you're going to name oxygen, you're going to name nitrogen. These are the like major components of the proteins, right? But like nitrogen is like a main thing which is present in the proteins other than carbon, hydrogen, and oxygen. Okay. And then we also have certain minor components like your sulfur, like your phosphorus. They're also present in the side chain of the proteins. But nitrogen is like a main thing. Is it clear to everyone? Are we okay till now? Okay, proteins are two types. Okay, we have globular proteins, we have the fibrous proteins. Globular proteins, where the polypeptide chain are very tightly folded, forming a globular shape. Okay, insulin belongs to this type of a protein. Okay, usually your functional proteins in the body, which have a proper function in the body, they belong to the globular proteins, like your plasma albumins. Okay, albumin, how it's a part and parcel of your blood, right? We recently spoke about osmotic pressure. you know Imagine, we spoke about the role of albumin in maintaining the osmotic pressure of the blood, right? And it's the albumin which does not leave the blood vessels. As a result, the osmotic pressure of the blood is maintained. So as a result, the fluid part of the blood never leaves the blood, right? The plasma never leaves the blood because of the albumin. So albumin plays a very, very important role in maintaining the osmotic pressure of the blood, right? So globulin, enzymes, they all belong to the globular protein groups. And then we have the stronger proteins, right? With the helical structure or the spiral structure, like your keratin in the skin, in the nails, and in the hair, hard and soft keratin, myosin, elastin, collagen. Collagen is like the largest amount of protein present in your body is collagen. Everywhere we have connective tissue in the body. We spoke about last semester connective tissue, right? So everywhere you will have collagen. It's binding everything in the body, connecting everything in the body. So collagen, the most important component of your tendons, your ligaments, your bones, isn't it? So that was about just the introduction of the proteins. Okay. So in short, we say that proteins are like so very important. And now to understand, what are these proteins made up of? These proteins are made up of something called as an amino acids. Okay. And then you might hear the word alpha amino acids. Okay. So what kind of amino acids what kind of amino acids make up the proteins? So the answer is alpha amino acids. Now your question might be, what are alpha amino acids? In order to understand alpha amino acids, let's first understand what is an alpha carbon. Okay, alpha carbon is something like, for example, if I have any functional group, like I have a bromine. Okay, bromine is connected to, for example, CH2, then we might have maybe another CH2. Okay, maybe I have CH3, something like that. Okay, so what is an alpha carbon? So before I can explain you what is an alpha amino acid, you need to know what is an alpha carbon. Alpha carbon is like, this is a functional group, alkyl group, right? So if you see here, this C is directly connected to the functional group. Okay, so if you see, this becomes my alpha carbon. So what is alpha carbon? Alpha carbon is the first carbon attached to any functional group, whatever functional group is here. Okay, so the carbon directly bound to the functional group is the alpha carbon. Okay, and then this will be, of course, the beta carbon, right? And this would be gamma carbon, right? That is the meaning of alpha carbon, right? Then what do you mean by alpha amino acids? Proteins are, if the question says that what are proteins made up of, you'll say proteins are made up of building blocks called as amino acids, and they all are alpha amino acids. So what are alpha amino acids? Okay, alpha amino acids is, if you see the structure of the amino acid, I think I had one more diagram for that. Give me a minute. It's okay, I'll just make my own diagram. Okay, give me a minute. I'm just going to open the blank page. Okay, new. I'm just trying to open a blank page. Where is it? Where is it? Next. I just need a blank page. Here it is, screen, white screen. Okay. So what do you mean by alpha amino acid? Okay. If you look at the general structure of amino acid, we have a carbon in the center. I have a functional group called COOH over here. Then I have another functional group called as an amino group, which is lying over here. Okay. And then I have a side chain, which is always, we call it R, and whatever is here, we're not bothered about it. And then we have H over here. Okay. So if you look at, this is my alpha carbon. If you see here, it's directly attached to the functional group COOH. Okay. So all amino acids, all 20 amino acids which we are going to study, which form your proteins, they are all alpha amino acids, because here the functional group, as you can see here in the amino acids, we have two functional groups, COOH and the amino group, right? So if you see here, this carbon is directly connected to the functional group. So this becomes your alpha carbon. So you can see that this alpha carbon connects the amino group to your acidic carboxyl group. And it is this alpha carbon to which R, NH2, COOH, and everything is attached to this alpha carbon. And that is why the amino acids which we have in the proteins, we call them as the what? Alpha amino acids. So all amino acids are alpha amino acids. Are we all okay about it? Did you all understand why we call them alpha amino acids? Any questions? Okay. Just let me know if you have a question in between, okay? Now, since I made the structure of the amino acid, who will tell me what is it? How many chiral carbons, or is the concept of chirality there in the amino acid? Are amino acids chiral? Yes. If you see here, this alpha carbon is attached to 4 different groups. So we have at least one chiral carbon in the all the amino acids. At least one chiral carbon is present in all the amino acids, except, we'll talk about the exceptional amino acids, right? There is one amino acid where we have an exception, and that is a glycine, where you will not see where we will have Instead of R here, in the glycine, we will have H here. That is the only exceptional amino acid, okay, which is not chiral. Rest all 19 amino acids are chiral. Are we okay till now? So we just said that all amino acids are chiral with the exception of the glycine. And we said that all 20 amino acids belong to a group called as an alpha amino acids, right? That's what we learned till now. And now we say that amino acids are amphoteric. What do you mean by amphoteric? Have you heard this term before? What is amphoteric? Amphoteric means what? Ampho. Ampho means, dual, twice. Oh, you have a very dual behavior, Ooh. So ampho means, person with a dual nature. You can remember it this way. So your amino acids have ampho behavior, they have an acidic group and they have a base also together. So the two functional groups which amino acids have are, one is acid, one is base. And this is a really important feature of the amino acid. Okay. Now, the amino acids, okay, which we have, okay, let me get back to the diagram. So that was all about it. Okay. Now the question is, so I just made that diagram of the amino acid because, because I know that you will not understand this diagram. But, if you have to simplify this diagram, you simply have to remove this H from here and put this H like this. That will make life easier for you. So this is my H, this is my R, this is my amino group, and this is my COH, carboxyl group, right? Now, you will always see, the thing which I made earlier, like, I made, oh, where is it? I lost my pen. Give me a minute. Okay. For example, this is my C, this is my R, this is my COOH, or this is my NH2, or what's wrong? Or this is my H. So you will never ever find amino acid in this form. Even though I wrote it like, R, NH2COH, H, but you will never find amino acid in this unionized form. Can anyone tell me what is the reason why amino acids are not present in this unionized form? What do you think? What could be the reason? Let me read it. Give me a minute. From in the body, acid and base, charge, stability, not stable form, because the presence of the acid and base in the same compound, it's not stable. Absolutely. Amino acids are never present in this unionized form. No. Even though you might write them in this form, but they will never be present in this form, because in nature, actually, unionized form of amino acid never ever exists. Because just now I told you that amino acids have an acidic group and they have an amino group. They have an acidic group, they have an amino group, right? So when you have an acid and base together in the same compound, okay, acid, proton donor, base, proton acceptor. So when they're together, this will be always ready to donate the proton. Okay, so the COH will try to give its proton to NH2 because it's an acid, it's a proton donor. Okay, while as your NH2 is a proton acceptor, right? It's a base, right? It will try to take that proton. Please give me that proton. While doing this business, what do they attain? They attain a charge, right? So your COOH, when it donates the proton, it becomes COO negative. Okay, and the proton which has been accepted by a base, while doing so, it got protonated and it became NH3 positive, which is called as a zwitterion. We'll talk about that in a while. So this is the form which is where whenever we talk about amino acid, they are usually present in the ionized form. You'll always find them with the charge. No matter what is the charge, you'll always find them with the charge. Is it okay till now? Did you all understand why amino acid exists as a zwitterine? I'm coming back to the zwitterine in a while. But first, the first and foremost thing is you should know that why amino acids are always in the charged form. Okay, because here, if the question says that what is the reason is because acid and base are together. Yes, Mariam, I will repeat. Acid and base are together in the amino acid. What does that mean? That means here we have a COOH. If you know the definition of acid, acids are proton donors. So the COOH will be always there to donate its proton here. So by doing so, this will become CO negative, and NH2 is a base, which is always ready there. Please give me that proton. I will take your proton. It's a base, right? So while doing that, it will take that proton and become the NH3 positive. So that is why you will find amino acids always in the ionized form with the charges. So in reality, they never ever exist in the unionized form. Is it clear, Mariam? So this is never ever present. Now, then the most important thing, if you remember when we discussed carbohydrates, we spoke about the penultimate carbon. Okay, this is a Fisher projection. Okay, so this is a Fisher projection for the amino acid, and this Fisher projection tells me that, oh, I have one chiral carbon over here. I have one chiral carbon over here, right? So these are the two enantiomers of the amino acids, because we just now said that all amino acids are chiral except glycine. All amino acids have at least one stereocenter except glycine, right? So they will definitely exist as an enantiomers, right? And we have the L form of amino acids and the D form of amino acids. Then Fisher said as that, look at the penultimate carbon. If the penultimate carbon has an amino group on the right hand side, you give it a name as a D amino acid. If the amino group is on the left hand side, you call it the L amino acid. So remember, we just said that one property of the amino acids was amino acids are amphoteric. They have acid and base together. And second thing, remember, first property we said amino acids are alpha amino acids, number one. Second thing we said that amino acids are all amphoteric. They have an acid and base together. Third thing we said that amino acids are always present in the ionized form, in the charged form. And the fourth thing you remember that the amino acids which we are going to talk about at least, which we have in our body, which are used to make the proteins, all of them, kullu, all of them are L form of the amino acids. In our body, we do not have D form of the amino acids. Please remember this forever. The 20 alpha amino acids, which we're going to talk about, which will be used to make the proteins, right? All of them, kullu, all of them are L amino acids. None of them is glycine have two hydrogens. We're going to talk about the exceptional amino acids, Gada, in a while. Right? L amino acids, Fahad, not the D one. In carbohydrates, we said them what? There we had, if you remember, if you go back to the carbohydrates, remember the triose sugar? Here we spoke about OH. If your OH was on the right-hand side, you call it a D glyceraldehyde. If OH was on the left-hand side, you call it the L1. So carbohydrates are never present in the L form. They're always present in the body in the D form. This was a question also there in the midterm, right? For amino acids, you will remember, we never ever have D form of the amino acids. All amino acids which are used to make the proteins, they belong to the L form. Is it clear, Fahad? Everybody? Okay. Okay. So if you're given the structures for both of them, the moment you see amino group is present on the left hand side, you have to say, okay, this is amino acid which is present in our body. This is used to make the proteins in our body. Okay. And then and then now this is like the question for this is like, please everyone pay attention. This is like everybody's emailing me and asking me that, do we need to remember the structures of the amino acids? No. Please pay attention what you need to memorize in these 3-4 slides. You do not need to know the structures of these amino acids, of course not. Not this one, not the other ones. Okay. But what you need to know, you simply need to know that if we have to classify the amino acids, you classify the amino acids as amino acid, because everything is similar in amino acid. Okay. Each amino acid will have a central carbon atom, right? Each amino acid, which is called as an alpha carbon, each amino acid will have an amino group. They will have a carboxyl group, right? They will have an H atom. But what differentiates one amino acid from the other is the R group. Remember that. It's the R group which is different, right? It's the R group which is different in different amino acids. That is why there are 20 different amino acids. Otherwise, everything is similar in them, right? So it's the R group which will differentiate one amino acid from the other one, right? Now, based on what R group, the red one which you see here, the side chain, based on what side chain an amino acid has, we have classified them into one. So you just need to remember the classification. Let me get a blank white screen once again. So amino acids have been classified. Remember the classification. Amino acids have been classified as non-polar based on what? If their side chain is hydrophobic, sorry, non-polar. So because their side chain is hydrophobic, okay, or amino acids are classified as polar. Of course, their side chain is what? Hydrophilic, okay, or uncharged. Or amino acids which are what? Acidic, okay, or amino acids which are basic. That's all you need to know as of now. Okay. And so you need to know the category, how they are divided. They're divided as non-polar, polar, acidic, basic, based on what side chain they have. Okay. Now, the next question which you might ask me, that do we need to know the names of these amino acids which are non-polar or which are polar, which are acidic, which are basic? Ideally, you have to, because that is what I said, or me, or we taught students, before also. We asked them to memorize, at least know the names. Don't know the structures, just know the names. Okay. For example, alanine, glycine, isoleucine, leucine, they belong to the non-polar one. Okay. And then the polar one, right? Cysteine, serine, threonine, right? And then the acidic chain, right? So for acidic and basic, you don't have to worry. We just have few of them. The only thing which you need to memorize is the polar and the non-polar one. And you just concentrate over. It's the same information, Lian. It cannot be different. Okay. So I repeat, you need to know the classification of the amino acid. You need to know we have amino acids as polar, non-polar, acidic, basic. Then you should know that if I ask you cysteine, is cysteine a polar amino acid or non-polar? So you should know that cysteine is a polar amino acid based on its side chain. We'll not go beyond that. Otherwise, there are many other concepts beyond that, but we'll not go beyond that. We'll stop over here. And the second thing, I will try to find a mnemonic, okay, which is there to help you, which can help you to memorize. Okay, okay, these come under the polar one. Or not only me, if you as a student, you find them, that's what we did last year. I had plenty of students. I used to tell them, if you find a good video, send it to me. We can share it with everybody. If you find a good mnemonic, send it to me. I can share it with everybody. If you find a good mnemonic, I will also find them. Okay, then we can go ahead and we can memorize that. Okay, so I'll just try to find a mnemonic. If I don't find that, then I'll let you know on Friday. Okay. Okay, let's concentrate on PPT as of now, Leon. Okay. I have never checked the book. Let me check the book as well. Okay, so remember what is there here in the slides. Okay, I will go back and check in the book, and if there's any discrepancy found, I will let you know on Moodle. Okay, is it clear? About no need to know the structures, just know the classification, just know the amino acids, that's it. Okay, so for example, if we have, for example, when we talk about the amino acids or the proteins which are present in the hydrophobic environment, of course those proteins will belong to those proteins. Those proteins will be made up of amino acids which have what, which have non-polar side chain, of course, right? So nothing else you need to know in these slides except the classification and except the names. And names, just leave it, concentrate on other things. Let me find out the mnemonic for you and then get back to you on this on Friday. Okay, so meanwhile you can study other things. But yes, I made a slide for you. Okay, this is super important because whenever we talk about amino acids, everyone should know everything about the exceptional amino acids. So we call these exceptional amino acids. Do you know what are exceptional amino acids and why do we call them exceptional? Let's talk about them. I made this slide so that you never forget this. Okay. Exceptional amino acid, point number one. Yes, I'm recording there. Yes, Yara. Can you see the red one blinking? Can you all see the red one? It says, I'm recording. Yeah. Okay, great. Thank you. Thank you for reminding, Yara. I'm already recording. Okay. So what are exceptional? Yeah, this you're supposed to know. Okay, not of course the structure, but yes, of course, why they are exceptional. Okay, what is there in these amino acids? What makes them exceptional? And the name, of course. So number one exceptional amino acid is a glycine. Why glycine is an exceptional amino acid? Because we just spoke about it. It doesn't have a chiral carbon, isn't it? Can you see a chiral carbon? No, it has hydrogen and hydrogen similar. So there is what? There's no, it's not asymmetric, it's symmetric, right? So that is why it is not chiral. That makes it special. Point number two, why do you think proline is special? What is so special about proline? What do you think? Why proline is special? No, it doesn't have two stereocenters. No, no. N bound to two carbon. Absolutely, absolutely. If you see N is bound to two carbon atoms, or you can say that proline is special because, see, I don't know whether about boys, but all the girls might know the amino acid proline because proline is something which improves our skin texture, which improves the collagen formation. In collagen, you will have most of the amino acids in collagen is the proline, right? So proline is which I think every female knows about the proline, right? Because it improves the skin texture. So that is how you can remember the proline. It is exception. It improves the skin texture. So what is so special about this? The speciality about proline is it has a ring structure as a side chain, right? So proline is the only amino acid where the side chain has a ring-shaped structure. Okay, thus makes it unique. So this is the only amino acid out of 20 which has a side chain, which is what? Which is a ring-shaped side chain. Okay, and if you see, if you observe it very carefully, this is my alpha carbon over here. right? This is my alpha carbon over here, okay? If you see here in proline, this side chain, which you see over here, it is attached to not just alpha carbon, it is attached to even your this nitrogen. So here, the side chain is attached to two groups over here, alpha carbon as well as this nitrogen over here. That makes your proline special. Because if you see rest of the amino acid, look at this. Glycine has a side chain attached to alpha carbon, only one atom. Look at this. Threonine, this is the side chain. It's attached to only one carbon, which is this alpha carbon. Isoleucine, it has a side chain attached to only one alpha carbon, because in all other 19 amino acids, the side chain is attached to the alpha carbon only. But proline is an exceptional one, because here the side chain is attached not only to the alpha carbon, it is also attached to the nitrogen of the amino group. Did I make it clear why proline is special? What makes proline special? Two things you have to remember. One, you have to remember that it is special because here this is the only amino acid where the side chain is what? The ring shaped. Point number two, why is it special? Because this is the only amino acid where the side chain is attached not only to the alpha carbon, it's also attached to the another atom, which is the nitrogen atom in the amino group. That makes it very, very special. Then comes your threonine and isoleucine. This is very easy for everyone to understand. You have to tell me why these two are special. Why did I bring them here in the exceptional amino acids? You have to tell me that. It has two stereocenters. Absolutely. It has more than one. If you remember, I told you that all amino acids have at least one chiral center, except glycine. But these two amino acids are there because they have what? They have one chiral center is this, another chiral center is, it has two stereocenters. It has two stereocenters. So as they have another stereocenter, can anyone tell me, is there a possibility of diastereomers here? Remember, in carbohydrates, we said that if there are more than one chiral centers, then there's a possibility of having diastereomers, right? We spoke about carbohydrates have a lot of diastereomers because they have more than one chiral center. So these are the only two amino acids which can have diastereomers. You don't have to know all that. I was just trying to relate it, what we learned previously. But in proteins, these amino acids exist as just a single diastereomer. There's no other stereomer possible, okay? But since they have two stereocenters, yes, there is a possibility of having many diastereomers, okay? And so, and proline is also called as an amino acid, just because of its unique geometry, which I explained. So these four are exceptional amino acids, which you should know why they are special and what makes them special, and other than that, the names, of course, but not the structures. So please, I've made it very clear. Do not send me again emails. Do we need to know structure? Not, you don't have to know the amino acid structure. Of course not. Okay. So moving on further, okay. Now we'll talk about what are zwitterions. Okay. So zwitterions are basically, see, you have to remember that, okay, when we talk about amino acids, okay, amino acids at neutral pH, or maybe at physiological pH, like 7 to 7.4, for example, okay, it might vary when we'll discuss about the isoelectric point as well, okay. So amino acids basically at neutral pH, they exist as a zwitterions, okay. As you can see here, zwitterions is a hybrid. Zwitter means a hybrid, a hybrid molecule which has both positive and negative ionic groups. Okay, look at this. So this is a zwitterion. I have a positive group as well as I have a negative group. So it's a zwitterion. Okay, but remember, even if it's a zwitterion, the net charge here is basically zero, okay, in the zwitterion, because the charges cancel out here. Okay, now even if I dissolve the amino acid in water, okay, the same amino acid, if the amino acid is in solid form, even if I dissolve it in water, it's going to exist as this zwitterion. Okay, but but it changes. What do you mean by changes? What changes? It changes, right? It depends upon, the charge on the amino acid depends upon in the pH of the solution. Okay, so pH of the solution plays a very, very important role in amino acids. But as zwitterions, they are present in solid state, or if you dissolve them in water, or at neutral pH, at physiological pH. They behave as these hybrid ions called as zwitterions. Okay. Now let's try to see what do these amino acids behave. Very important thing. So please pay attention. Understand the concept. Then rest of the things are easy. So how do they behave if I dissolve them in a medium which is highly acidic? Okay, I made this slide so that you never forget this. In strong acidic pH, amino acids are always positively charged. They behave as cations. But you have to ask me how. Show us how. How is it possible? I will show you. Number one, I said that if I dissolve an amino acid in a solution wherein I keep on adding HCl, I keep on adding HCl to such an extent that the pH becomes zero. Oh my God, highly acidic, right? So in a strong acidic environment, okay, what will happen to the amino acid? That means if this is your amino acid in the strong acidic environment, what will be surrounded with, guys? In the acidic environment, what do we have everywhere? My amino acid will be surrounded by a poor amino acid. Oh my God, you put so much acid in me. I have everywhere what? Protons, 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 right? I have everywhere H positive ions because I dissolve the amino acid in highly acidic environment. When you have protons everywhere, then do you think the COH is going to control? What will the COH do? Yes, guys. In presence of so many protons, right? What is the COH going to do? It's going to get lose H? No. Neutral? No. Once again, no, 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 no. Get H, gain H, absolutely. This, remember that the COH is hungry. Yes, except protons, gain proton, absolutely. Remember that this poor COH is hungry for a proton. It needs proton somewhere, right? And I gave this amino acid a feast. I dissolved this amino acid in a highly acidic pH where he has protons everywhere. So he's hungry for protons. What is this amino acid going to do? The COH is going to get protonated. When you accept a proton, what is it called? That means it's going to attain this hydrogen, okay? Or you can say the strong acid is going to donate a proton to COO negative. And what will happen to COO negative? It's happy now. It got its proton back, and now it is COOH. Isn't it? It's happy now. It's happy go fellow now. And now the only charge left with my Zwitter ion is the positive, and positively charged ions are called as a cation. Did you understand why did I say that amino acids behave as cations at highly acidic pH? So remember this verse forever. The question says that in strongly acidic pH, how do your amino acids behave? They behave as a cations, and you understood the reason how. Is it clear to everyone? What happens in acidic environment? Okay, wonderful. Let's do the opposite now. Let me dissolve the amino acid in the basic environment. Now, first of all, you have to tell me as a chemistry student, you have to tell me that what do you mean by basic environment? What does a base have? pH is absolutely higher. OH, absolutely. Now, please pay attention, everyone. So I'm going to take the same amino acid once again. This is my amino acid, and now this time I dissolved it in a strong base, which has a pH of about, my God, 14 pH. So what is surrounding here? OH, OH, OH. Lian, don't worry, I will repeat it, don't worry. OH. What do you expect? What's going to happen? What's going to happen? Guys, girls, since there are a lot of OH, okay, so what's going to happen in the environment? This NH3 is like, I have an extra proton, please. I just want to get rid of this extra charge. Yes, it will get deprotonated, absolutely. Because this ion over here, it has extra this proton and it wants to get rid of this extra charge. I don't want to have this proton. So please take it away. So this is going to give off a proton to OH and make OH happy. As proton will be donated to OH, OH will become what? It will become H2O because it happily got a proton from the NH3 positive, right? And while it donated, it got deprotonated. Remember the words, because sometimes the question might be asked about the protonation and deprotonation. You should know when will it get protonated, when it will get deprotonated. Even though you know the concept, but maybe you don't know the words, you will be confused then in the exam. So it will get remember, if you want to take down the notes, you can take down the notes. An amino acid gets deprotonated when it is dissolved in the strong base, right? And now why, and it will in the strong base, the amino acid will behave as a anion, as you can see here, because CO has still a negative charge over here, right? So it's going to behave as an anion in the strong base, which is a negatively charged ion. I'm going to repeat it. I'm going to repeat it now. Okay. Is it clear till now? Do you have any questions till now? So no, you have to know the vocabulary as well. Okay. So I repeat once again. I said that in the strong acidic pH, if the pH is very, very strong, okay, the amino acid behaves as a cation. Why it behaves as a cation? Because in the environment, we have a lot of protons and your COO negative is going to accept a proton. It's going to be protonated. So here, COO negative will be protonated. It will accept the proton from the surrounding, right? And thus become what? Let me erase all this. And thus, it becomes what? Without any charge. And why is it cation? Because we still have a charge on NH3, a positive charge. So protonation in the acidic pH, and in the basic pH, it will be deprotonated because the NH3 is going to give off its proton to the surrounding environment. Okay, so just don't go beyond, don't confuse yourself with many things. Just whatever I'm teaching you, just kind of remember that as of now. Okay, don't try to ask yourself why this, why not this. There are plenty of other things which can also happen. Okay, but I'm not going to touch all that. I'm just going to tell you the crisp thing, which is which is a basic concept. If your basic concept is clear, then you're all okay. Okay. So Sarah, Sarah says that, Sarah, I told you that. how will a zwitterion behave? What happens in a zwitterion? The charges are going to cancel, Sarah. I told you that, right? The charges are going to cancel out in zwitterion. I think I explained that. The charges are going to cancel out here, isn't it? So what will be the net charge on the zwitterion? Guys, in the zwitterions, it's going to cancel out, right? It will be zero, absolutely, right? But yes, okay, if we change the pH of the solution, which I'm not going to explain you all that, that's not even required here. If we change the pH of the solution, then the net charge on the amino acid is going to depend on what is the pH of the solution in which it is dissolved, because then the net charge changes. Remember, zwitterion has what? As I said, the charges cancel out, right? So it has zero net charge. But if I'm going to dissolve it in a less pH or a greater pH, these are going to be changed. It depends upon which one will be protonated, which one will be deprotonated. We will not go into all that. So that is why no need to do this diagram, because we usually give problems on this, so no need to do this diagram, because we're not going to give you pKs and all that. And usually we used to give the but in UPP we never give the diagram, because that will be too much for a UPP student. Okay, so nobody's going to give you problems on this, if the pH of the solution is this, and tell me what is the net charge of the amino acid. Of course not. Okay, so okay, so each amino acid will have a pH, will have some kind of pH at which it will behave as a zwitterion. Do you agree? Yes or no? Each zwitterion is going to have any pH, not necessarily a physiological pH. It might vary, it also depends upon what is there in the side chain, right? So, but as I told you, at physiological pH 7 to 7.4, the body pH, right, amino acid exists as a dipolar ion, which is a zwitterion. Okay, but any amino acid or any protein, this holds not only for amino acid, but this holds for the proteins as well, because by the end of the day, amino acids are made out, proteins are made out of amino acids, right? We're going to talk about in a while about the proteins as well. So there the same concept applies, the zwitterion and everything is the same thing. Okay, so there I'm not going to explain it. So whatever we have learned here in amino acids, it's going to be same in the proteins. It's going to hold same true for the proteins as well. Okay, so any amino acid or any protein, okay, at a particular pH, at a specific pH, it's going to behave as a zwitterion, or it's going to behave as a hybrid ion, where it has what? Both positive as well as a negative charge. Is it clear? Now, what is that pH called? What is that pH called? That special pH, okay, that special pH where your protein or your amino acid, okay, I repeat, that pH where your amino acid, okay, or your protein, okay, is, exists as a zwitterion or a dipolar ion and has no net charge, that special pH is called as the isoelectric pH or isoelectric point. And how do we write it? We write it like this: a small p and this I, okay? A small p like this and a capital I. So what does this show us? This tells us that this is an isoelectric pH or an isoelectric point of a protein or the amino acid. At this point, it behaves as a zwitterion, okay, where it has a number of anions and the cations. What are anions and cations? The positively charged ions and the negatively charged ions on a particular amino acid are equal. and the net charge is 0 over here. As long as the pH is Noor physiological pH. But then if there's any change in the blood pH, Noor, if there's any change in the blood pH, you will combine this with the respiratory system. If carbonic acid, if I have more carbon dioxide in the blood, that means I have more carbonic acid in the blood. That means there is more H positive ions in the blood. How will my proteins behave, Noor? Only Noor will answer. If I have more carbon dioxide in the blood, that means I have more carbonic acid in the blood. That means pH is low. I'm telling you pH is low, but you have to tell me how will my amino acid proteins behave then? Think again. How will my proteins behave? As a cations or as the anions? Noor. Think once again. Proteins are in the acidic pH. There are a lot of protons around. When there are a lot of protons around, what will happen to the amino acid? What will happen to my proteins in the blood? Suppose it's a plasma protein. What will happen to it in the acidic pH? How is it going to behave? Noor. Cation. Sara, thank you. Noor.
Doctor, I don't really understand the question.
I
Can
said
you
you
please
asked me a
can you
question,
please repeat it?
how is my how is the amino acid going to behave in the blood?
Yeah.
Right? I told you if I decrease the pH of the blood, how do I decrease the pH of the blood? What if I have more carbon dioxide in the blood? If I have more carbon dioxide, that means we have more carbonic acid in the blood. So I have more
Yes.
acid in the blood. So blood is going to be acidic or basic? The pH of the
Acidic.
blood is going to reduce. It's not going to be 7.4. It's going to be lesser than 7.4, right?
Yes.
So if you have less pH, how will your protein behave in the blood? Cation or anion?
Cations.
Cation. That was the answer.
Yes,
Did you?
doctor, because I answered acidic. So I
No,
thought like you
no.
meant it's
No.
basic.
No. It's not about acidic and basic. I was asking you, how is your protein going to behave? I know the acid environment is acidic. You're right. Absolutely right. You're right. But how is your protein going to behave? It's going to behave as a cation, right? And what if the pH, for example, will increase in the blood?
Anions.
Absolutely. Very good. Absolutely.
Okay, got it. Thank you,
Got
doctor.
it? Thank you, dear. So did you understand now?
Yes.
Thank you, dear. Yes, of course, Tanya. Your physiological pH is 7.4, right? But then sometimes, the pH is going, it has to be 7.4, right? But sometimes, it might go up or it might go down. We will study that in respiratory system. If we have more carbon dioxide in the blood, the pH is going to get down. Then your excretory system and the cardio and your respiratory system will respond and quickly bring the pH back, bring the homeostasis. Okay, Tanya? Because you have to maintain the 7.4 pH in the blood, because at this pH your proteins are stable in your blood. Okay. Okay, is it clear to everyone now? Okay, so you know what is an isoelectric pH now, right? What is an isoelectric point now? Okay, absolutely. So so at this isoelectric pH, they will behave as zwitterions, or you can say that at this pH, they will not even migrate to the electric field because their net charge is 0 at this point, isn't it? At isoelectric pH, the net charge is 0. Okay. If you will, apply electricity to them at this point, they will not move to anywhere. They will not move to any electric field because their net charge is 0. Okay. And now this is a table. Okay, now the next question. Do we need to memorize these isoelectric pHs of different amino acids? The answer is no. You need to know what is an isoelectric pH, what happens at this pH, right? But you don't need to know what if we would have given you problems, then only there was a requirement of, memorizing the isoelectric pHs of various amino acids. Did I make it clear? Okay. So what effect will be on the solubility and buffering capacity of the of the proteins or the amino acid at isoelectric pH? The solubility and the buffering capacity will be minimum, right? Proteins are least soluble at their isoelectric pH. Just remember it. Okay, no need to connect it with something, other concepts. So that was about the isoelectric pH. And then you can just read the physical properties. This is all the same thing, what I explained it to you. Okay, at neutral pH or physiological pH, they exist as zwitterions. Okay, they are solids with high melting point. Just memorize all these. Okay, they are fairly soluble in water. Okay, net charge on the amino acid depends on the pH of the solution, which I already told you that. Okay, dissolving an amino acid in water, it will become a zwitterion. Okay, so remember, isoelectric pH, okay, if it's neutral, the amino acid is a zwitterion. In basic environment, it behaves as an anion. In acidic environment, it behaves as a cation. That's what you can remember it forever. Okay, and amino acids are amphiprotonic, right? They act as both acid and the base. Did you all understand? Are fairly soluble, like slightly sparingly soluble. You can't say that they're soluble. You need to heat them. For example, when I used to work in the lab, if I have to use the amino acids, I used to use different solvents to dissolve it. As I said, that pH depends upon that. And then sometimes you need to kind of give a slight amount of heat, because they get denatured at high heat. Okay, so that was about. So did you all understand? I will repeat once again. Let me show you here so that you don't forget it. Give me a minute. Let me have a screen, white screen. So I'm going to write it here so that you don't forget it. So at isoelectric pH or at neutral pH, the amino acids, they act as zwitterions, right? With net charge 0. Point number 1. In basic medium, okay, it's going to get deprotonated amino acid. So your amino acid will behave as an anion. Clear? Who will tell me what happens in the acidic medium? In the acidic medium, they're going to behave as they're going to get protonated. So they will behave as the cation. So if you just want to take a picture of it or write it down, so this you can remember it, keep it in front of your eyes, and you will never forget this, right? So here they will get protonated, okay, and here they will get deprotonated, right? Am I correct? The NH3 is going to lose one proton, and it will result in the formation of water and form water. Okay, shall I explain the next topic, guys? Everyone, any questions till now? Are we okay? Okay, so we're going to move to the next one and show. Keep it. Okay, where were we? Okay, now some other amino acids. I told you earlier we need to know uh, the amino acids which are exceptional, right? We spoke about glycine, proline, as well as threonine and the isoleucine. But then you also need to know some amino acids, which are again important. Why they're important? As I told you, you don't need to know about every amino acid, but yes, the amino acids which are exceptional, they have something different in them. Okay. And one of that is your, one of among this group, we usually call them as amino acids where you need to pay more attention. One, I told you exceptional amino acids, and now I'm going to explain you about a couple of more amino acids where you need to know that, which are where you need to pay more attention. Okay, why more attention? Because cysteine is an amino acid which is so very important, which enjoys a special place, in proteins. Why special place? Because this is the only amino acid which has a which group? Sulfhydryl group, also called as a thiol group. If you're a chemist, you will identify this SH. SH is a thiol group, right? So this is the only amino acid which has a thiol group. And because of this thiol group, the two amino acids which might be present in a polypeptide chain, okay, you will see that in a while, okay, when we'll discuss the different forms of the primary structure and secondary and tertiary structure of amino acids, right? This is one amino acid, this is another amino acid. Excuse me. So this amino acid has a side chain which has a sulfhydryl group. Okay. I got a slide over here. Look at this. This amino acid has a sulfhydryl group in its side chain. This now amino acid also has a sulfhydryl group in its side chain. Both of them will react and will form a sulfur-sulfur disulfide bond. Very, very important. Why this bond is important? Why did I say very important? What is the significance of it? Because you will see that in a while when we'll talk about different structures of the amino acids, you will see that it is this sulfur-sulfur disulfide bond, okay, which is binding the two cysteine residues together, and these two cysteine residues together can connect the two polypeptide chain. If I have one polypeptide chain, another polypeptide chain, here also I have cysteine, here also I have cysteine, their side chains will going to interact and they will form a what? Sulfur, sulfur, they'll form a disulfide bond. And it's this interchain disulfide bond which is going to be very, very strong anchoring point, holding the two chains together. Remember, guys, this is very important point to note. It is, yeah, it is not a peptide bond. You can remember that it is a strong bond, like a covalent bond. It's not a peptide bond, Faisal. Okay, but it's a covalent bond. If the question says that what kind of bond is a disulfide bond, the answer should be it is a what? It's a strong covalent bond. Like the peptide bond is also a covalent bond. Yes, Mohammed. They have a, because of their side chains, they can interact with each other. They can interact, two amino acid chains, can be connected by these disulfide linkages. Sometimes just one amino acid. I have one cysteine here, I have another cysteine here. They can also be connected by these disulfide bonds. So we call that an intra-chain disulfide bond. So even one chain can be connected to each other by the disulfide bridge or disulfide bond. Yes, Muhammad and Muhammad, both the Muhammad square. Is it clear? So it's not necessary that you can have disulfide linkages only between two polypeptide chain. You can just have two cysteine in the same amine in the same polypeptide chain can also interact with each other. We call it disulfide linkage. Are we clear? And why they are important? Because they can hold the chain very strongly together, very strongly. So it helps in the tertiary structure. We're going to talk about that. Okay. And thanks to cysteine, because cysteine has a thiol group, cysteine has a sulfhydryl. You call it as thiol or sulfhydryl. Don't get confused if you have a question saying thiol group is present, true and false. Thiol group is present in the cysteine, true and false. You might be thinking, what is a thiol group? She never said anything about thiol group. Sulfhydryl or thiol is the same thing. Okay, guys, everyone, and girls, everyone, are we okay till now? So it results in the formation of a cysteine. As you can see here, two amino acids together, they form. So that is why cysteine has always received an extra, attention. Okay, because it stabilizes the structure of the polypeptide chain. Moving on to the few other, as I said, there are few other amino acids which needs more attention, which are not exceptional, but yes, they need more attention. Okay, sometimes the question says that name the amino acids which contain sulfur. Sometimes the question is there, name the amino acid which contains sulfur. So the two amino acids in the entire 20 group which has sulfur is your methionine and the cysteine. Remember this as well. Cysteine, look at this, cysteine has a sulfur, right? And then there's one more amino acid called the methionine, the first amino acid in the polypeptide chain. It also has sulfur in its side chain. Okay, sometimes questions like this also come. No, no, this bond will be, no, Sham, this bond will be only formed, of course, if they're close to each other, right? Imagine if you don't have cysteine and cysteine close to each other, then of course not, it will not be formed then. Okay, Sham? Okay. Okay, moving on the other amino acids, okay, which are moving the other amino acids, which are basically, yeah, I said, Mariam, sometimes the question says that name the amino acids which have sulfur in their side chain. So the only two amino acids which have sulfur in their side chain are methionine and cysteine. Okay, methionine and cysteine, Mariam. Okay, now the other amino acids. Okay, what are the other amino acids? Amino acids with the aromatic rings on their side chain. You know what is an aromatic ring, right? As you can see over here. Okay, so for example, we have here phenylalanine, tryptophan, and tyrosine. Okay, so when we talk about tryptophan, you no need to know structures, remember the names. Tryptophan is like a precursor, like a grandfather for the neurotransmitter serotonin. So whenever your body needs serotonin, okay, the origin is going to be the amino acid called as tryptophan. That is why it's very, very important, right? Because we know that serotonin is a neurotransmitter which helps in mood enhancement, right? And God forbid, if there's less serotonin in the brain, it leads to the depression. Okay, so that's very, very important. Okay, so epinephrine, is it clear till now? Okay, so just remember that the tryptophan is the precursor for the neurotransmitter serotonin, and remember the function of the serotonin. Okay, that makes tryptophan special. Okay, and then we have other amino acids like your phenylalanine and tyrosine. Phenylalanine, if you see here, phenylalanine can also give rise to tyrosine, as you can see over here. Okay, simply you need to do oxidation over here, so phenylalanine can be converted into tyrosine. Okay, so why are these amino acids important? Because they are precursor to the epinephrine and norepinephrine. You know what is epinephrine, norepinephrine? Okay, we already know about that, right? The adrenaline hormones we already spoke about, right? They're produced by the adrenal medulla, right? Yes. So that's why phenylalanine and tyrosine are important. Okay, and I told you also that tyrosine can also be obtained from the phenylalanine. Okay, dopamine is also a neurotransmitter. Okay, and this dopamine is involved, whenever the reward system. I will explain all that in neurotransmitter chapter. I think we have that all that here, but we don't have to know in detail the function of dopamine. Okay, what is important, you have to know that, okay, we have, the phenylalanine and the tyrosine, they are precursors to the epinephrine, norepinephrine, right? And and the function of epinephrine, right? So you can I don't need to explain that. Okay, and the second thing which you need to know here is tyrosine can be also obtained from the phenylalanine. Okay, And then other than that, okay, what else you need? So I just said that tyrosine is derived from the phenylalanine. Okay, so tyrosine is sometimes called as a non-essential because you don't. I'm not going to explain because it's not in your book what are essential and non-essential amino acids. In short, uh, non-essential amino acids are those amino acids which are synthesized in our body, which are made in our body. So we don't need to have them in food. Okay, but the essential amino acids are those amino acids which should be present in our food because our body do not make them. Okay, so that is why we need to take them in the form of food. So just remember the definition. You don't need to know which are essential, even though there is a slide at the end, but you don't need to know that. Okay, it's not there in your book. Okay, so tyrosine is sometimes called as a non-essential. Why non-essential? Because we can produce it from the phenylalanine. So the question says something like that. Can we produce tyrosine in our body? Yes, we can. We can produce it from the phenylalanine. That is all you need to remember, not more than that. Okay. And then some different amino acids which are actually not amino acids because we don't use them in the protein synthesis. Okay, so we call them as the uncommon amino acids because they are not there in the protein synthesis. Okay, we don't use them in the protein synthesis. For example, the oxidation of proline can form hydroxyproline. So we don't use hydroxyproline in the amino acids. So we're not concerned about that. Okay. Same thing, the lysine can be converted into hydroxylysine. We don't use hydroxylysine in the amino acid. So it's an uncommon amino acid. But yes, if you remember, I don't know whether you remember it or not. Remember when I said that, if you remember when we were discussing goiter in chapter 9, if you remember, I told you that I had a picture, a lady in her neck. She had a big lump in her neck. I don't know whether you remember it or not. I told you that, thyroxine, okay, is not a non-steroidal, hormone, but since it's originated from an aromatic amino acid, which is it originates from the tyrosine, which is an aromatic amino acid. Connect your chapter 9 with biochemistry. And if you remember, I told you the goiter will, the female with such a big lump in her neck. Why? Because she was able to form tyrosine. Unfortunately, when you don't eat iodine, okay, what's going to happen? The active form of thyroxine will not be formed. That is why she had that big lump in her throat, because she did not eat food which was rich in iodine, because iodine is very much required for tyrosine to be converted into the thyroxine. A very important point to note here. So that is why if you remember, I told you long back, people never used to eat, people used to have we used to have a lot of patients with the goiter. Then government realized that, and now the salt which we eat is all iodinated, just because they realized how important iodine is for the thyroxine hormone, right? And then they realized how important thyroxine is for all other systems of the body, be it your nervous system, be it your reproductive system, right? Be it for the growth and development, especially for children, right? Connect your PHSF with biochemistry. So did you see how important iodine is? Now look at this. This tyrosine will not be converted into thyroxine unless and until you eat iodine, because iodine is the part and parcel of its structure. Is it clear to everyone? Guys, is it clear? And girls? We learned that in chapter 9 as well, right? Okay. So these amino acids are formed either by oxidation of the amino acids, or by the iodination of the amino acids like your tyrosine. Okay, then we get these uncommon amino acids. Okay, then what is a peptide bond? Who will tell me what kind of bond is a peptide bond? What do you think?
Covalent bond.
It's, yes, I said that it's a type of a covalent bond. Okay, and this bond is formed when your because your proteins are formed of amino acids, when your amino acids are joined together, okay, it results in the formation of a peptide bond. It's a partial double bond, okay, so that is why we say that it is a covalent bond, and formed between the what, between the carboxyl group of one amino acid and an amino group of another amino acid. You should know all these things, and not only what is a peptide bond, you should also know that which groups are involved, right, in the formation of the peptide bond with the dehydration of water. Absolutely right. So it's a bond between a carboxyl group and an alpha amino group. Okay, it's a kind of amide bond, but since this amide bond is present in the proteins, so that is why we call it a peptide bond. Remember, it is a stronger bond. Okay. So if you see here, look at this. This is one amino acid. This is another amino acid. The carboxyl group of this amino acid, the amino group of this amino acid, right? They will form a peptide bond, as you can see over here. Okay. And then the amide bond in the peptides and proteins are called as, what is the answer for this? The amide bond in peptides and proteins are called as? What is the answer to this question? It is called as a peptide
bond.
Peptides bond.
Absolutely, absolutely. You guys are super duper intelligent. So till now we are okay. Are we okay till now? You're comprehending everything. No issues till now, right? Alhamdulillah. Okay, good. Good. We're going good. We finished almost half of the chapter. We have half of the chapter still left. Okay. Okay, now how many amide bonds will a dipeptide have? So of course, if I have one amino acid, another amino acid in a dipeptide, okay, how many amino acids how many bonds will I have? One, right? Tripeptide will of course have what? 1 and 2, isn't it? Okay. Other than that, what else you need to know is the convention. This is the same thing, peptide, dipeptide, tripeptide. So in short, you have to remember that the peptide, for example, when we say dipeptide and tripeptide, di means, two amino acids together. Tri means three amino acids together. Okay. So we sometimes call them as, oligopeptides, the way we said in the monosaccharides. Okay. So oligo means up to 10 amino acids together. Okay. So polypeptide means where you have almost, 10 to 50 amino acids together. We call it a polypeptide chain if it has 10 to 50 amino acids. Okay. Almost. Okay. A polypeptide chain. Okay. And then protein which is something very, very long. Okay. If you remember when we were discussing chapter 9, we had some hormones as peptides and some hormone as proteins. So the hormones which were peptides, that means they had shorter chain of amino acids, whereas proteins are always greater than 50. Whenever you have more than 50, remember these numbers, guys, everyone. Whenever you have more than 50 amino acids in a polypeptide chain, you will call it a protein. Okay, you will call it a protein. And sometimes the individual amino acid is also called as a residue. Don't be surprised if you hear the word residue. Residue we use, for one amino acid. Okay, residue. Two residues are joined together. That means two amino acids are joined together. Okay. Now, how do we write them? It's always about, the way in English we write from left to right. For, the correct way of writing an amino acid and a polypeptide chain is we write it from left to right. Okay, so we'll start from here to here. Okay, so here we'll have an N terminal and here we have a C terminal. Very important. What do you mean by N terminal and C terminal? N terminal means on this side I have this amino group present, a free amino group present on this side, right? And on C terminal means I have a free COOH group. So you will always write amino acid from N to C. Everyone, from left to right, N to C. Is it clear to everyone? So end of the protein chain will always have, if a question says like this, end of the protein chain will always have dash dash. And the choices are amino group or the carboxyl group. What will you choose? What will you choose? The carboxyl group. Very good. Absolutely. It is the carboxyl group. Wonderful. Okay, so look at this. This is my N terminal. This is my C terminal. Okay, that's how the polypeptide chain is connected. That's how you know from N to C. The way we spoke about 5' to 3' in DNA, right? Same on 3' we will always have OH group, right? Same thing for here as well. 5' will always have a phosphate, free phosphate group, right? So same thing for here as well. You know, the conventions are very important. For example, if I ask you to write Arabic from left to right, will you write it? Never. We will never write it from left to right, right? We will always write it from right to left. Yes, Reem, good morning, dear. Dear, whatever you have missed, it's perfectly okay. I have recorded the session. I'm going to upload it on Moodle, okay? So you can listen to it right from the beginning. I don't remember what question did I ask, Mariam. What was the question? I asked you. I asked you what is present at the end of a protein chain? Is it a carboxyl group or an amino group? What will you answer, Mariam? Carboxyl, isn't it? Don't worry about the attendance, Reem. Your names will be automatically recorded. Don't worry about that. Today's class is not about attendance. So I'll give attendance to everyone. Don't worry. It's more about, revising, because the midterm is up, midterm is there on Sunday. Okay, so don't worry about the attendance today. Okay, so no need to go into details of this slide. Whatever I explained you, that is important, right? Just remember all this, okay? It's basically kind of, if you remember, I told you that, the peptide bond is a partial double bond. That is what, which was explained by the linear spalling. Okay, it has a 40% double bond character. That is what so you can take down only this information up to here, for example, up to here. Okay, so you can remember that it's a partial double bond. It's a covalent bond, right? Which was found by linear spalling. What is an isoelectric point of a pH? Who will explain me? What is an isoelectric point? Yes, Island, please answer. Yes, dear, please go ahead. Island.
It is neutral, so it have a negative and positive. That is mean the charge it will be 0.
Yes, the net charge will be 0. So what, if you have to define it, what is it? The isoelectric point is that pH where the number of anions and cations on a protein will be equal in number. Remember? Yes, it has no net charge, absolutely, right? No charge. It exists as a zwitterion. No net charge. It's 0. Very good, right? Very good, all of you. Thank you, Island dear. Thank you. So I'm not going to explain you all this. This is whatever I explained you about the amino acids. It's exactly the same thing about the proteins. Of course, proteins will also behave as zwitterions. They will also have isoelectric pH because they are made from the amino acid. So I'm going to skip this, but that does not mean you will also skip it, because this is the same thing what I explained you about the amino acid. You will read all this. You will memorize all this. Okay. So we know that the proteins in the blood act as a buffer, and we know now why they act as the buffer, because they can resist. I gave an example. Somebody asked me a question about pH, right? Noor, she asked a very good question. So I gave you an example. If you have more carbon dioxide in the blood, which is going to, because carbon dioxide is present in the form of carbonic acid in the blood, it's going to decrease the pH of the blood, right? So thankfully we have proteins over there which will act as the buffers. Okay. Now the second part of the chapter. We just finished half of the chapter. Now we have the second part of chapter. Now I want all of you to pay attention. The second part is equally important. Okay. So don't think that this is the end of the chapter. This is equally important. The way, for example, imagine if I would teach you cardiovascular system without teaching you anatomy of heart, would that be okay? Can I teach you cardiovascular system without explaining you anatomy of heart? Of course not, right? Exactly. Similarly, this part of the chapter is, I know that, when students study something, by the time they reach to the end, they are like, oh, this is not important. This will not come in the exam. She will not give, or he will not give this in the exam. You will not think like that. And you know that I've always told you, we always give questions in the scattered form. We try to touch every topic. So don't leave any topic. Study all the topics. Okay, guys and girls? Clear? Should I start with the second part of the chapter? I really wanted to give you a break, but we are not eligible for break. We will have a break once we finish this. Before starting enzymes, we will have a short break. Don't worry about that. You want a break, Faisal? Okay, 3-minute break for Faisal. Don't worry. Okay, so take a 3-minute break. Okay, because we can't afford more, because we need to study one more chapter. We just finished half of the chapter. So just take a water break. Even I will take a water break. I need water. Faisal, don't worry. Welcome back. No, Fatma, I sent you an email. I sent you an email that you will not be considered as late. I don't want you to miss your other classes. I said that tomorrow Dr. Karyapur or anybody should not tell me that, or Dr. Amjad, that she missed my class saying that I have a combined class in P Bio. Please don't do that. I sent you an email also about that. Please stick to your schedule, everyone. Please stick to your schedule, because you have an option of listening to the what do you call it, recording in the evening. Of course, you have to. That's why I sent you an email yesterday. Please stick to your own schedules. If you don't have a class at 9, you can start. You can start at 9. No worries. Yes, I will, Lara. Yes, I will. Definitely, I will. Okay. So should we start? Is Faisal, are we ready? Are you back? Okay. Okay. Now this is again a very important part, because polypeptide chains or the amino acid make up something protein. So it's very, very important that we know what is the structure of the protein. Okay. So we know that protein has a primary, secondary, tertiary, and quaternary structure. Now, before I explain it to you, you need to know all these structures very, very carefully, right? You need to know all of them because they're very important. As a biochemist, you should know what are these structures. You should know everything about them, okay? So first of all, so please pay attention, everyone. What is a primary structure? Primary structure is defined as the sequence of amino acids in a polypeptide chain. Simply, okay, for example, if I say that this is serine, this is valine, okay, this is histamine, right? Okay, anything, right? So, or glycine, proline, whatever, right? So this is basically the sequence of amino acids in a polypeptide chain, which is always read from N terminal to the C terminal, which I already explained it to you. So this is called as a primary structure of the protein. Now, okay, very important thing, that how is, for every structure you have to know what maintains that structure. You have to know about the bonding. If not the explanation of a bonding, just the name of the bonds, okay, everyone. So when I say that, how is your primary structure going to be maintained? No, there's a different way, Mohammed. We call by Sanger's method. We make up, we find out, in lab, if you get a chance to work in a lab, we have many methods to know the, it's totally different from the DNA sequence. No, DNA sequencing is different and protein sequencing is different. We have a Sanger's method to know the protein sequencing, and many other methods are now available. Yes, we can know it in the lab, Mohammed. Okay, it's not the same as a DNA sequencing, of course not. Okay. So now moving on, what stabilizes? As I said that in all the structures, as I'm explaining you, you need to know that how is that structure maintained? The bonding, bonds you should be knowing about here, the name of the bonds. So the question says that what stabilizes your primary structure? So you have to simply say that, okay, I will not tell you, you tell me, what stabilizes the primary structure? Absolutely, Faisal. Very good. It is the peptide bond, right? It is the peptide bond. It's the peptide bond which is stabilizing the primary structure. But then, if you remember just now, we also spoke about there is a chance that if you have a single polypeptide chain like this, if it has a cysteine here and cysteine here, if they're close to each other, so then this chain can also be, stabilized by the intra-chain disulfide bond. So you can say that if there's no option about disulfide bond, so you can select with your eyes closed that it is a peptide bond, right? But yes, if there is an intra-chain, link between the two parts of the same chain, then we can have a disulfide linkage also stabilizing the primary structure of protein. Okay, is it clear to everyone? So it also includes the position. It's not only like I have serine, valine, histine, glycine, proline. No. If in the another amino acid chain, I have valine, then for example, I have glycine, then I have histine, right? And then for I have serine. Okay. So does that mean I have the same amino acid in my second polypeptide chain? Is the first one, the second one similar? Of course not. Look at the order. The order is different. Here I have serine, valine. Here I have valine, glycine, histine. It's something like, like the DNA chain. If I have adenine, thymine, guanine, cytosine, right? In the other chain, I have adenine, guanine, cytosine, thymine. So the order also matters. The position also matters. Okay. The position where your disulfide bond is, that also matters in the primary structure. Okay. So the sequence of amino acids in a polypeptide chain is very, very important. Okay. No need to know all this. Nobody's going to ask you about all this. No need to know all this. Okay. So moving on further. Okay. Now you all know about the hormone insulin, right? First of all, tell me which organ or which gland in our body produces insulin in our body. It is the, absolutely, it's the pancreas. In the pancreas we have the beta cells. Absolutely, very good. Now when we talk about the hormone insulin, we have the two polypeptide chains together, and this, let's say this is an A chain and this is the B chain. Okay, so as an example here, they have shown that the insulin has a dash kind of structure. Insulin has a primary structure. Okay, and it was first time identified in 1955 by the Sanger. Okay, so now, as I said, that insulin has two polypeptide chains, and the two polypeptide chains, as you see, they are also interlinked with each other. Do you see here? Do you see how disulfide linkages are stabilizing the two chains? This is an interchain disulfide bond, and this is an intrachain. Intrachain is like, as you can see over here. Now you need to know the positions as well, because I told you the positions are also important in the primary structure of protein. So just remember that the two polypeptide chain of the insulin, okay, they're stabilized by the disulfide linkages, okay. And if you see here, the disulfide linkages are present either interchain, okay. If I count it here, this is maybe seventh one, I think, yeah, between 7th cysteine and 7th cysteine here. Okay, 7th A and 7th B. And then as I go down, 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 look at this. This is 20th cysteine. And here this is one above, this is 19. So remember this 20 and 19. Numbers should be, you should know the numbers as well. So I will repeat. The interchain disulfide bond between polypeptide A and polypeptide B of the insulin, you have the disulfide bond between the 7th cysteine and 7th cysteine of both the chains. Then between 20th cysteine and 19th cysteine of both the chains, A and B chain. Is it clear? The interchain bond. You have to know the positions as well. Okay. And number two, if you see the intrachain, look at this. Let me erase this now. Just remember the numbers, nothing else. Remember the numbers. That is it. Okay. And what else? Yeah, it might be different because the sequence, because this is not a human insulin. This is a bovine insulin, which we get from animals. It might be different, but for bovine insulin, if you get it in the exam, it will be exactly what's there in the book. We'll not go beyond that facet. But it might be definitely different because the sequence of human insulin is a little different than the insulin in animals. Okay, and this, look at this. Who will tell me this intrachain disulfide bond? It is between 6 cysteine, isn't sixth one? This is 5, this is sixth one, and between the 11th cysteine. So here you will remember 6 and 11. Here you will remember 7 and 7. Here you will remember 20 and 19. That's all you need to remember here. Okay, remember the numbering. Okay, so answer to your question, Faisal, look at this. There's a slight difference between the human insulin, a very, very slight difference between human insulin, cow insulin. You know that before we started getting insulin, by the recombinant DNA technology, now how we produce insulin is we have the gene, we got the gene from, we sequenced the gene from the humans. Okay, we took that gene and put the gene into the plasmid. Okay, this is the insulin gene which we got from the human, and then put this plasmid back into the bacteria. Okay, now our bacteria is making more and more insulin for us. That is how we are getting insulin nowadays, as a medicine. But this was not always the case. Long back, we used to take the pancreas of animals. Okay, kill the animals, take their pancreas, remove the alpha cells, purify it, and make the medicine out of it. So that is why both of them are almost similar. Okay, it's showing you here. Look at this. It's almost similar here. Is it clear to everyone? Okay, so here this is a table with 4 different types of insulin. Okay, but there's a slight difference between the two. Then moving on, it's just trying to tell you how important primary structure is. Guys, don't take primary structure, don't take this guy easily. Primary structure is very, very important, because all your other structures, whether we talk about the secondary and the tertiary structures, they all are built up, based on your primary structure. It's something like, if you're going to make a house, okay, you will have a foundation, isn't it? Then you will make first floor, second floor, third floor, 10th floor. But if there is no foundation, can you make a big building? Can you make a big building? Of course not. Of course not. So remember, that's why I said that no matter what happened, I know secondary, tertiary, quaternary structures are also important, but primary is like the very, very important, because without it, you will not have the higher order structures. Okay. And then it's just trying to tell you the vasopressin, the ADH hormone, and the oxytocin hormone, right? These two hormones, it's just trying to tell you, look at this. They have identical structures, including their disulfide bonds are similar, but they just have a slight difference in position number 2 and 7. And then I will not discuss their function. You already know the function. You should know the functions of them, right? You know how important your ADH is, and you know how important your oxytocin is, isn't it? But look at this. Everything is same in both the hormones, except if you see here, what is the difference here? At position number 2, we have here arginine, right? And here it has leucine. Remember the positions. Okay, remember the position number 7 is also different in these two hormones. That shows us how important the primary structure is. That is not all. If you go back and discuss the hemoglobin, right? If you remember this slide from your PHSF, look at this. In the normal beta globulin chain, you had glutamic acid here, right? And here we have valine. That changes the life of a person. If they have valine at position number 6, then they have what? They're suffering with a sickle cell anemia. You should know all these things. All this is, I'm not going to explain it in detail because I explained that in PHSF. So you know all this, but you will read all this. Don't think it will not be there. Yes, you have to read all this. Okay. So it's basically trying to tell you that every sequence in the polypeptide chain is important. Even if one sequence has gone wrong, one amino acid is not there, it will result in the disease formation. It will cause the disease in a particular organism. That is it trying to tell you. Okay. This is also, this is, and if you remember, I don't know about boys, if you remember guys, when I was teaching you blood chapter, okay, if you remember, I told you, no, when I was teaching sickle cell anemia, did you remember I told you about hydroxyurea, how we treat the patients with the sickle cell anemia? We give them hydroxyurea. Do you remember? It reverts what? I have explained all this in PHSF in detail. So you will study this once again here. Don't think I did not explain it here, so it will not be there. Yes, it might be there. The fetal hemoglobin, remember? I told you since they have a defective what beta chain, so we give them hydroxyurea. Hydroxyurea basically does what? It basically changes their what? What does it change? Who will explain this? Hana, Tasneem, can you? Island, yes, please go ahead, Island. I explained that in PHSF.
It is promote in the marrow bone and produce alpha cells,
Alpha
not
chain.
beta cells.
Alpha
Alpha
chain.
chain, not
Okay, very good. Wonderful. So because the fetal hemoglobin does not have a beta chain, isn't it? The problem with the sickle cell anemic patients is the problem is they have a problem in the beta chain, that this beta chain is defective, right? So by giving hydroxyurea, what do? We give them fetal hemoglobin, right? And fetal hemoglobin does not have any beta chain. You see, it has 2 alpha chains and 2 beta chains. Okay, so hemoglobin has what? 2 alpha chains and 2 beta chains, right? And the people who have sickle cell anemia, they have a problem in their beta chain. So what do? We give them hydroxyurea, which basically increases what? They don't have this hemoglobin, they have the fetal hemoglobin, HbF. So in the HbF, instead of having 2 beta chains, they have 2 alpha chains and 2 alpha chains and then 2 beta chains, sorry, gamma chains. There's no beta chain here. So that is why, these patients, they, their survival is increased, their symptoms are reduced till they have the fetal hemoglobin in their blood, right? So it kind of, you dilute it. Their body, their bone marrow will still produce the wrong chain, the wrong beta globulin chain, but it's just that we have a lot of I know 2 alpha and 2 gamma chains there, so it's kind of getting diluted here. Okay, so we reduce the sickling effect in these patients by giving them hydroxyurea. Okay. So after studying primary structure, what can we say? We can say that primary structure is very, very important because it tells us what? It tells us the sequence of the amino acid. It is maintained by the covalent peptide bond, right? Also by the disulfide linkage. We said that the positions of the disulfide linkages are also important, as we discussed in the insulin. The position and the location of the disulfide linkage, we should know about that. Okay, and then we discussed how ADH and oxytocin, right, even though they're similar, but the slightest difference in their primary structure makes them 2 different hormones, right? And then we discussed that any problem with the primary structure of a protein, right, it will interfere with its biological activity. What does that mean? That means a person can get a sickle cell anemia if there is any change in its primary structure. That is all we spoke about, that about the primary structure of the proteins. Okay, now moving on to secondary structure. What will a secondary structure tell you? Okay, secondary structure is basically, as it says, it's secondary. Okay, it is about the the steric relationship. You know what is a steric relationship? Do you know what is a steric relationship, guys? Arrangement, the 3D arrangement, right? Okay, so it is basically the secondary structure is basically it tells you how your amino acid chain, longer amino acid chain folds upon itself. Okay, and remember the bonding, as I said, that secondary structure is mainly stabilized by your hydrogen bond, and that to hydrogen bond where? In the backbone. Remember that. Okay, it is stabilized by hydrogen bond. Is hydrogen bond a covalent bond, guys and girls? Hydrogen bond is not a, no, it's not a, it's a weak bond, but there are plenty of hydrogen bonds which stabilizes the secondary structure of the protein. Okay, it tells us the configuration of a protein, okay, about, there are few amino acids which are far apart from each other. It tells you what is their configuration. Okay, how these, for example, how amino acids are close, we'll just talk about alpha helix and beta pleated sheets. You'll get to know, what I mean actually when I say that, amino acids which are close to each other, in the vicinity of each other, in the, people who are neighbors. For example, if you have the next door neighbors, you and your next door neighbors, you will interact with each other. So same is your secondary structure. Your neighbors who are very immediately living next to you, okay, your amino acids which are next to you, which are living next to the polypeptide chain, how they're interacting with each other, that tells us the secondary structure of the protein. And that secondary structure of protein is very, very important because it defines the physical properties of the proteins. You will see that in a while. We'll talk about the keratin. The keratin in your skin is softer and the keratin in your hair is harder. It has the secondary structure. Okay. So it tells us about the physical properties of the protein. So that is why secondary structure is also important. Okay. So let's talk about what is an alpha helix and what is a beta helix. So remember, these are the two motifs. So you can say these are the two subunits of the secondary structure. So alpha helix is like, as you know, it's a helical structure simply, right? Look at this. The way we said about DNA, that is an alpha helix. Okay. Where if you see here, I told you the neighbors. Who are the neighbors here? This amino acid, guys, please pay attention. It's so very important, everyone. Okay. So I told you, remember, whenever you remember secondary structure, remember your neighbors. Okay. When your this neighbor and this neighbor, how they're going to interact with each other. They're going to interact by the hydrogen bonding here. This amino acid and this amino acid, how are they going to help? How are they going to interact with each other? Remember your neighbors. Hi, hello, how are you? You tell them every day because you're close to each other. Do you understand what I'm trying to say? This amino acid and this amino acid, they will react by the hydrogen. These are all hydrogen bonds. This is your alpha helical structure. Is it clear? Did you all understand the alpha helical structure? Stabilized, there's no covalent bond here. And remember, the bond is between the backbone. This is the backbone, not in the side chain. Very important point to note down here. The hydrogen bond is not in the side chain. The hydrogen bond is the backbone. Because when I will move to the tertiary structure, there again, I will talk about hydrogen bonding, but there the hydrogen bonding is between the side chain. I repeat, alpha helical structure is stabilized by the hydrogen bonding, point number one, between the neighboring amino acids, the neighbors, right? But then second thing I told you that here you have to remember the hydrogen bonding is present between the backbone, right? Not between the side chains. Is it clear to everyone? Any questions about the alpha helical structure? So the keratin, which is a fibrous protein found in your hair, nail, horns, they all have the alpha. So you have to remember the examples. Remember the structure, remember the bonding, remember the examples, and remember the positions in the insulin. Okay. So when we say keratins, okay, so there's a difference between the keratin in the skin and the keratin in the hair. Keratin in the skin is a very soft, elastic keratin, okay, while as keratin in the hair, okay, is having a, a little stronger than, than the other one, than the present in the skin. Okay. So keratin overall is not very elastic, that it's not very elastic. But then, you might have another alpha structure called as a fibroin in the silk. Silk is kind of, it has, it doesn't have alpha helical structure, it has a beta pleated sheets, so it's a little stronger than the alpha helical one. Okay. And what else you need to know about it? I think that's all you need to know. Nothing much about it. We discussed the bondings and we discussed the example, the keratin. I think that's all. Okay. Okay, then you will read all this. Okay, how many amino acids? So just read all this. 6 amino acids are there per turn of the alpha helical structure. Okay, they are all in same plane. Okay, the NH groups, they point in the parallel direction. So just read all this. Okay. And R groups are outside. If you remember, I told you only the bonding, the hydrogen bonding is between the backbone, because if you see here, the R groups are outside. They're not facing into the backbone. They're pointed outside. Okay, this is an important point to note here. Okay. Any questions about the, you will just read this. Just read this. Okay, how many amino acids per turn? Maybe there might be a question like this, But what is the basic thing which I wanted to tell you, you understood that about the alpha helical structure, correct? Any question about it? It's a helical structure, spiral structure stabilized by hydrogen bonds in the backbone. Okay, most stable conformation, stabler than the beta pleated sheets. Remember all these. Okay, R groups are always from the outside. You know why R groups are outside? Because as you can see here, they're a little bigger than these other atoms. So that's why R groups are like, outside. There's no place for R is like a fatty person. So the backbone says that we don't have place for you. You are a fatty person. Just stay out. There's no place for you. So backbone has no place for R. That is why R is outside. I'm just trying to give you a few things, few points which can help you to memorize, that R groups are, moving outside. There's no place for them. No place for R groups. Okay. And what stabilizes them is that the interchain hydrogen bonding or the intrachain hydrogen bonding. Let me see how many of you can answer. What kind of hydrogen bonding we have in the alpha helix? Intra or interchain? Intra, as you can see, absolutely, absolutely. Intrachain hydrogen bonding, absolutely, guys, very good. Okay, so then the beta pleated sheets. Okay, in beta pleated sheets, what do you have? Okay, you can have two chains. So please pay attention. You can have two chains like this. This is one polypeptide chain with the N terminal and the C terminal. And then you can have another polypeptide chain with the C terminal and the N terminal, right? And then please pay attention again, what will you have? Hydrogen bonding, or what else you can have, guys? It's stabilized by yes, it can, let me see the answers. This is not intra. They're two different chains. This can't be intra. They're two different. This is, yeah, interchain. This is one chain. This is another chain. Correct? Right? This is one chain and the other chain. So again, in the secondary structure, as I said, that here again you will have the hydrogen bonding, which can be an interchain hydrogen bonding between the two polypeptide chains, or you can have a longer, a single polypeptide chain. Like for example, if I have a longer like this, if this is a longer one, which folds like this, okay, then it folds like this. Do you see what I'm trying to do? It's just one polypeptide chain, isn't it? So this is my N terminal, this is my C-terminal. What kind of bond do I have here? Is it inter or intra chain? It is the hydrogen bonds between the intra chain. Absolutely, it's the intra chain hydrogen bonds. It's not intra. I want you to be very careful about intra. Intra means when you have one chain, and bonding is within the chain. Intra, within, inside. Inter is when you have two different chains. Then you will have bond between the two. That is interchain hydrogen bond. This is intra, okay, and this is inter. Am I clear about it, everyone? Am I clear about it, everyone? Oh my God, I can't. Yes. Helix is just one. It can be long, it can be longer as well. Absolutely. Mohammed. Okay. Any question about it? So again, as I said, that you have to remember one thing, that secondary structure is stabilized by hydrogen bonding, which is a non-covalent bonding. Okay. And look at this. These amino acids, which are, they're neighbors. Neighbors are interacting with each other. The same thing I told you about for the secondary structure. You will remember the neighbors, they are interacting with each other. Okay. It defines the organization between the amino acids, which are very close to each other. That defines your secondary structure. Okay. So then you can just read all this. Okay. What else is there? Just read it, just read it. Whatever was the basic information I explained you that, it's just telling you, for example, it's just telling you that if you see here, the R groups over here, okay, in one chain, it alternates, if you see it alternates, this is like, beta pleated structure is like a, staircase. The way you have your staircases, right? It kind of resembles that, the beta pleated sheets. Okay, so the R groups on one chain, they alternate with each other. Okay, as you can see here, one is below, another is above, one is below, another is above, one is below, another is above, they alternate with each other. So you just read all the information. But whatever is important, I told you, and this is an important slide. Here I have mentioned it so that nobody gets confused between the secondary and the tertiary structure. I've mentioned the hydrogen bonding is between the backbone, right? Not between the R groups over here. Whereas in tertiary structure, we'll talk about the hydrogen bonding is between the R group. This is the basic difference between the secondary structure and the tertiary structure, which we're going to talk about now. Okay, and then we have a random coils also. Do you know what is a random coil? Lian, in beta chain, we have both intra as well as inter. Lian. Yes, Mohammed. The secondary, yes, it can be parallel and anti-parallel. Yes, Mohammed, you're right. You can have a beta pleated chain, one going this way, like Mohammed, N and C, and other going this way. I'm sorry, other going this way, N and C. So these are two anti-parallel beta pleated sheets. Mohammed, is it clear? We can have them anti-parallel as, yes, of course. Okay, Sham, inter is like, inter is like, okay, I'll tell you one thing. Inter is like, if, for example, if you have a friend, join your hand with your friend, with your sister who's around you. That's interchain hydrogen bond. Okay, Sham. And then when you join your right hand and the left hand, that is an intra-chain. I hope I gave I was able to explain in a very simple way. And this you will never forget, Sham, now. Remember, you joining your right hand and the left hand is an intra chain, because the bond is between your right hand and the left hand within one chain. Whereas an interchain is, no, it can be intra and intra. It can be both. It can be both. As I gave you both the examples. In this is an example A, Okay, let me make it in a different way. Sham, interchain is when you have like a polypeptide chain and then when you have a B polypeptide chain. So this is an interchain. Sham. Intrachain is when you have a long polypeptide chain. Look at this. This polypeptide chain is folded, it's getting folded. Look at this. So this is my intrachain. This is my intrachain. Sham. This is intra. Is it clear now? I just have one polypeptide chain here. But here I have two polypeptide chains. They can be parallel or they can be anti-parallel. Did you understand now, Sham? Alpha helix is intra. Yes, it's only intra. Yes, dear. This is what I'm talking about, the beta one. This is the beta pleated sheet. Alpha is only intra. Yes, dear. It's only intra. Got it? Okay, great. Okay, now, so what is a random coil? Okay, random coil is like, don't take this random coil guy easily. Random coil is, so pay attention. If I have, for example, random coil is like, I have one beta pleated chain and then another beta pleated chain. Okay, sometimes these two chains are connected with each other by a linker. Do you see the blue one is a linker? Okay, so this is my beta pleated. This is also my beta. This can be parallel or anti-parallel. So they're joined by a small kind of a polypeptide chain. So we call this as a random coil. Do you all understand what is a random coil? So random coil is just linking the two anti-parallel strands or maybe parallel strands of the beta pleated sheets. There's no bonding thing, in the random coil. No, it doesn't have a secondary or any tertiary structure. Okay, it doesn't have. I mean, it is in the secondary structure, but it doesn't have any bonding. There's no specific bonding. There's no bond in the random coil. That is why the word random. Okay, is it clear to everyone? What is a random coil? You don't have to remember any bonding pattern in the random coils. Okay. Okay, moving on further. So many globular proteins have all three kinds of structures. Yes, there are some globular proteins which can have alpha helix also, beta pleated sheets also, and random coil. Look at this. You see the color combination. I have an alpha helix here. Okay, and then I have the beta pleated sheets here. Okay, as you can see here, this is the alpha helix. Okay, and then I have the beta pleated sheets over here. Look at this, these ones. Okay, and then you can have the random coil. Look at this orange ones. See, all three are connected by the orange coils. So they are like a random, random coil. They're called as a random coils. So the protein can have all the three structures together. Now examples, as I said, you have to know the examples as well. What about collagen? What is so special about collagen? As I told you that collagen is a protein present in our connective tissue. Remember, tendons, cartilages, bone, teeth, bones, right? Everywhere you have collagen. Even blood vessels, they have connective tissues, right? Wherever you have a connective tissue, you'll have a collagen. And I told you that this is like a very important protein because it's the most abundant protein in our body. Okay. And what kind of structure does the collagen have? Remember that collagen, okay? So please pay attention, everyone. Please, everyone. Collagen, as you can see here, it has the how many chains are together in collagen, guys? How many chains are together in collagen? Excuse me. How many helices? Triple helix. It has a triple helical structure, isn't it? That is why it's stronger. Look at this. One, two. It's a triple helical structure. Okay. Now an important point to note here. Collagen has three polypeptide chains and joined to each other in the helical manner. But what is the amino acid composition of the collagen? Collagen has a uniqueness. What is a uniqueness about the collagen? Collagen has a uniqueness, and that uniqueness is what? This is the amino acid. This is the, this is the protein which has almost 33% of this protein has, which amino acid? Just glycine. Remember the glycine one? It has like most of the amino acid present in this protein is the glycine. You can say that every third amino acid is a glycine. Can you see here? I have glycine, then I might have valine, I might have, histidine, whatever. Then I have again glycine. Okay, then other two, then again glycine, right? So there is a repetitive sequence here, or there's a repetitive amino acid, which is a glycine. Every third residue here is a glycine. Is it clear to everyone? What you need to remember about the collagen? To remember, it's a structural protein found in the connective tissue. It's the most abundant protein. It has a 3 helical polypeptide chains joined together, and it is very, very rich. I'm sorry. Guys, I, just give me 1 minute, okay? I'll just have water. Give me 1 minute. Yes. Okay, so I was just telling you that. So which amino acid is rich in the collagen? It has glycine. Every third amino acid here is the glycine. Okay, but then in the primary structure, you might also have the proline or the hydroxyproline, but glycine is the most common amino acid in the collagen. Okay, any other question about the collagen? Do you know something about collagen? What do we use it for? What do we made out of animal bones? What do we get? If we boil collagen, what do we get out of if we boil collagen? Yeah, tightening of, yeah, it has a triple stranded helical structure. But when we boil it, you might have you ever heard about gelatin? How do we get gelatin? When they burn, when they boil animal bones or animal skin or something, what do we get? Yes, when the solution of a collagen is boiled, it changes the, yes, it changes the viscosity. Absolutely, it changes the viscosity of the solution. It becomes more and more thicker, more and more thicker. Okay, because its native structure of your triple helical structure is altered. Okay, and then we get a random coil structure. Okay, and that is a gelatin, which we use. Yeah, absolutely, absolutely, yes. So remember that is basically a what? A triple helical structure which has been boiled, it was destructed, and then now it's just a random coil. Okay, and then I told you glycine is very common. The reason why glycine is very common, because glycine is very smaller amino acid. It can easily fit here inside. So that is why glycine is more common in the collagen. Then we'll talk about the tertiary structure. Who will tell me about tertiary structure? Why is tertiary structure important? Do you think it's important for proteins to have tertiary structure? And what about the bondings? Why everybody is silent? Tired, guys? We're just about to finish. Tertiary, quaternary, and then denaturation. Maybe another 10 minutes we'll finish it. It's a structure where the proteins are biologically active. Okay, very good. What stabilizes this? For the function of the protein. Okay, very good. You see, it's a 3D structure of the protein. Okay, the higher order structure of the protein is a tertiary structure. okay, wherein you have a polypeptide chain, you know, it folds upon each other, okay. A tertiary structure of a protein tells us about the nature of that protein folding, you know, how protein is being folded in that particular protein, okay. You can say it tells us about the overall arrangement, okay, of everything, you know, the interrelationships between everything, okay. So that is why this structure is very important, because it's the most stable conformation of the proteins, okay. And if you remember, I told you the difference between secondary and tertiary is here you will have the hydrogen bonding also between the R side chains, okay, not only between the peptide backbone but also between the side chains, okay. So this structure is very, very important because it tells you the overall conformation of a polypeptide chain. Very, very important. Now these things, just remember the names. Where is it? Remember what stabilizes your tertiary structure. Remember just the names, okay. So the covalent bond stabilizes it, of course, right? Because you will definitely have a cysteine bond, right, between between the thiol group of the cysteines, okay, because cysteine will be there in the side chain. They will have a thiol group in the side chain, okay. And then of course hydrogen bonding also stabilizes it, okay. And the salt bridges also stabilizes it, okay. And then just remember the names and the hydrophobic interactions, okay, and the metallyl coordination. So all these things stabilize the tertiary structure. Just remember the name. Okay, so it's not only covalent, we have both covalent and non-covalent interactions stabilizing the, yes, stabilizing the a particular, you know, protein. Look at this, we have every kind of interaction here, every kind of, so we have a disulfide link here also, we have a metal ion coordination here also. Look at this, we have a helical structure also, we have where we have the intramolecular hydrogen bonding. Look at this here, helical structure, okay. So here we have the side chains hydrogen forming the hydrogen bond. This is special about the tertiary structures. The side chains, they form the hydrogen bonding over here, okay. And the electrostatic interaction. So we have plenty of things in the tertiary structure of the proteins. And define what are chaperones, okay. Once the protein is produced by the, yeah, once the protein is produced by the what do you call it, by the process of translation, okay. But then these proteins, they also undergo into the post translational modification. What is the post translation modification? So once the protein chain has been formed, okay, there are certain proteins which are like, you know, helper proteins, okay. Those helper proteins are required for folding a particular polypeptide chain, and those are called the chaperones. What are chaperones? Chaperones are the proteins which help in the folding of the polypeptide chain. Remember, God forbid, if the protein is not folded, look at this. This is an unfolded chain, and this is a folded chain into alpha helical structure. God forbid, if the chaperones will not be able to fold the chain, and God forbid, it can cause diseases. Okay, like Alzheimer's disease, you know, and Alzheimer's disease, which is not well understood what exactly is the reason, but the possible cause is that there is a misfolding, okay, of a protein, okay, which is called an amyloid protein, which is very, very important for the nervous system, okay, very, very important, you know, for the growth, okay, you know, in the neural repair in our brain. That amyloid protein is misfolded, which causes the, you know, the Alzheimer's disease, okay. So remember, protein folding is very, very important, and chaperones play a very, very important role in folding the protein. Without them, the proteins will not be folded, and they will not be the functional proteins unless they are folded. Then the last one is a quaternary structure. Quaternary structure is something like, you know, not all proteins can have quaternary structure, of course not, okay. In some proteins, you know, they can have quaternary structure, but it's not a part and parcel of every protein will have it, okay. Remember that. For example, hemoglobin, it has a quaternary structure of protein, Okay, we have two alpha chains and two beta chains. Or the fetal hemoglobin, right? The two alpha chains and the two gamma chains. It's a quaternary structure. Or immunoglobulins. Do you remember we studied about immunoglobulins, two heavy chains and two light chains? Remember the lymphatic system? The lymphatic system, two alpha chains and two beta chains. Yeah, that is a quaternary structure. Okay. And in the enzymes, we will study about the lactate dehydrogenase. It's a tetramer. It has four polypeptide chains, right? So not every protein will have a quaternary structure. Okay. So those proteins which have more than one polypeptide chain, as I give an example of hemoglobin, immunoglobulins, only these proteins will have the quaternary structure because these chains will fold upon, okay, and they will result in a functional protein which is called as a quaternary protein. Okay, and remember for the quaternary protein, God forbid, if we have, for example, alpha chain and the two beta chains, right? They are very, very important because if these subunits are dissociated, the whole protein is dissociated. Okay. And what stabilizes the quaternary chain, as you know that you need to know the stabilizing, what bonds stabilize the quaternary, chain, right? You have the hydrogen bonds. Okay. You have the electrostatic bonds, you have the hydrophobic bonds, you have the salt bridges, van der Waals forces, all these also stabilize. Remember the names. Stabilizes the quaternary structure of the protein. This is just showing you the structure of, heme. Okay, I think that's all. Even the integral membrane proteins, they also have the quaternary structure. Okay, remember the examples. That is it. Okay, and the last topic is denaturation. Okay, what's denaturation and what causes it, and what happens if a protein is denatured? What will happen, guys and girls? What will happen if the protein is denatured? It loses its function. Absolutely, it loses its function, right? So, okay, I'll ask you a question. Yes, Aileen, please go ahead. What happens if you denature a protein?
Destroyed protein by many things, like مثلا, for example, heat, rise the heat of the proteins.
Very good. Okay. What happens? You're absolutely right. But what happens if I increase the temperature of the protein? They will get denatured, right? What will happen then? Which structures are destroyed, unfolded, bonds are
The
disrupted?
bond,
Yes.
the bond between protein will be destroyed.
Absolutely. Very, very important thing which you have to remember. Very good. When you heat a particular protein or when you denature a protein, the secondary, tertiary, quaternary structure of the protein are lost. What will happen to the primary structure, guys and girls? Will the primary structure also be lost? Yes or no? No. Remember it forever. You take your egg. What do? You have your egg. Egg has nothing. It has a protein inside, right? So albumin is a protein. So once you heat your egg, once you boil your egg, what happens? Does it have the same consistency after you boil it? No. Before boiling, the outer part was transparent, was liquid. But once you boiled it, it turned into white solid. That means protein got precipitated. So that means all its secondary, tertiary structure was lost. But the only structure which will not be lost will be the primary structure. It is still a protein there, even though it's an aggregated protein. It's no more functional now. But remember, denaturation, whether you use the heat, just read all these things, whether you use the heat, remember all these, remember the names. Everyone, please remember the names. Okay, remember the heat, urea, surface activated like detergents, reducing agents like mercaptoethanol. We use this in the lab, to denature the proteins. Okay, heavy metal ions, alcohol. Nowadays, what do? We all use alcohol before entering the house or after going out of the house. Everywhere we have sanitizers with us. They have 70% alcohol. What does that alcohol do? That alcohol is simply going to denature the proteins of the bacteria or the viruses, right? The protein, the outer protein, uh, you know, uh, you know, capsule they have. Okay, and once proteins are denatured, it makes holes in the bacterial cell wall, and khalas, bacteria is gone for a toss, right? So remember all these agents, and remember that all the structures could be lost by denaturing a protein, but the only one which is preserved is the primary structure. Remember the boiling of eggs, we still have that white colored protein even though it's precipitated, but we still have that. Okay, with that we finished proteins. Oh my god, any questions? It took us like 9 to 10, 10 to 11, 2.5 hours to finish proteins, and we just have enzymes now. But guys, did it help you? Did this revision class help you? Did you all understand? Are we okay?
Yes, thank you. You
Thank
helped us a lot with the 2 chapters.
Mashallah. We have now, enzymes. We'll take a 10-minute break because I don't want to, kind of, overburden you all. Just take a 10-minute break. You can have your snacks or whatever, okay? Water. And it's 11:35. We'll come back by 11:45. Would that be okay? And then we'll start with the enzymes.
Yes, okay, thank you, Doctor.
Thank you, everyone. Okay. Okay, so we'll take a 10-minute break and come back for enzymes.